All right, so here is our the multiple imputation output. It gives you the number of imputations you ran. And overall, and so there's kind of like the missing data patterns again. 6 out of the 10 variables had missing data, 4 had complete cases. Remember, there was 117 cases that had complete data, so 83 cases had at least some type of missing data. So you can see this kind of gives you more of your missing value patterns. It gives you just some more information about your imputation. We imputed gender, type of program, reading, writing, math, and science scores. We didn't make any imputations for race, SES, school type, or social studies scores because they have complete data, remember? So we didn't make those. And so then it just tells you, the type of, female was imputed using a logistic regression. These were the independent variables in the model. It had 18 missing values, so we imputed 36 as we requested. We requested 2 values. So we really don't need much from that. What we want to do is then use the SPSS MCMC diagnostic macro that's available on Canvas. Let me open up that diagnostic macro. What you'll want to do in here, there's only 2 areas that you'll want to change. You notice in here on the slash folders, you need to give the file path to the folder containing the parameters.sav file. So this is where I put it in my missing data folder. And then you give it what are the variables in the parameter.sav file. It only includes your scale variables in that file. That's why I added drop categorical variables. So these were all the scale variables in the file. If you're not sure which variables in the file, just open up the parameters.sav file and you can see that for yourself. So you could do that, and then you could run the macro from here. Just highlight everything on the page and run it. Or you could make those changes, save the file. If you know where you have it saved, you can use an insert file command. And then I'm just going right to that file, and I'm saying to insert that syntax file and just run everything in it. So let's do that. Okay, that output is done. So this gives you some information on whether the model converged or not. And so you get just some text info. You notice it says every model on here converged at each iteration. Well, it's checking it for at every 100th iteration. For 1,000 iterations. Did the model seem to converge? This is a graph of what all of this is here. It looks like after about the 200th iteration, it started to stable off some. As long as it was over what he's saying, the value of 1.05, then the model's converged. So we don't have any problems with that. What we're looking at here, assessing convergence, we're really looking at 2 things. One, did the model reach a stable distribution? By that we mean, did the predicted values remain pretty stable across time? There doesn't appear to be any type of trend in the analysis. And then we want to know, well, how long did it take to reach, a stationary plot? So, main thing what you're looking for is that these trace lines look like a random scatter, or, just not a random scatter, but, or random random lines going up and down. If you see stuff that's sort of like trailing off, you know, the pattern starts going off here or going down, indicates that something's wrong. We want to know that we've reached what they call like a stationary posterior distribution. We want to know that the distribution that we're sampling from isn't continuously changing. Because you know what we're doing is, instead of, you know, we're trying to predict reading scores, basically using a logistic regression. Well, instead of just, you know, if we, you know, based on just using that regression line, all the predicted values are going to fall on that line. Well, instead of doing that, we're basically randomly sampling from like a distribution of the residuals. So this is really what they would call like a Bayesian regression analysis, and we're sampling from what they call the posterior distribution. So we're running the regression analysis, and then adding a little bit of, you know, predicting what the value might be, and then adding a little bit of variation to it by taking a sample from the posterior distribution of that analysis. So, you know, the goal of this, you know, this algorithm that's run these imputations, is to basically like simulate random draws from a distribution. So we don't want the distribution to keep changing. If that's the fact, that's what would indicate if this was like trailing off up or trailing down, or is making some type of pattern instead of just, you know, random lines here. You know, this random pattern sort of indicates that the distribution that we're sampling from then is stable, and that's what we want. So we want to see that the distribution is stable. We want to know, well, how long did it take to reach this stable distribution? And here it looks like it happens almost immediately. So if you start seeing a pattern up in the beginning, and then it starts to trail off into like a sort of random pattern, then you'd want to look down here at like, okay, around like the 200th iteration, it seemed to sort of stable off. This one seems to stable off almost immediately. So that indicates that the model then converged to a stable distribution. Some reason that you could have convergence problems. One reason could be that, you know, we just cannot estimate writing scores. You know, the data we have just aren't doing a good estimate of what the writing scores might be. It could also indicate that, you know, the number of missing data is too great for that variable. You know, one thing maybe to just, if we really don't need that variable, can we eliminate it somehow? Can we maybe use some type of logical imputation to, you know, get some more information back in that variable? So typically, convergence problems mean there's a problem with your imputation model, and it indicates that there's a problem with that variable, that we're not doing a good job of estimating its missing values. So it's going to do this for both the mean for the variable, there's the mean, and then the standard deviation. And so you'd want to look at both of these and kind of judge with all of them. They all seem here to be a nice random, you know, random plots. So the distributions seem pretty stable. And they all seem to converge, I'd say, pretty quickly. So, you know, I think maybe starting at, you know, every 200th iteration may not be a bad idea, and that's typically what Enders recommends. So it looks like we're not having any problems with the model convergence. So we'll go back then to our syntax and actually run the the multiple imputation. So since we have evidence is converting, let's run our imputation analysis. Let's open up our missing data file. It'll close out all those other data sets that it opened up to create those plots. And then here's some syntax in to run the multiple imputation. We can see here, so the command is multiple imputation. You include all the variables that you want to, but the variables you want to impute and any of your auxiliary variables here. So it looked like, we converged pretty quickly. So at, about 200 iterations, we'll then take a sample from that posterior distribution. We're going to impute 20, do 20 imputations, and I'm going to change the scale model to predictive mean matching. That's what this represents, and that's one of the things Van Buren recommends. Predictive mean matching is really great instead of just using like the linear scale model. That's SPSS's default, because it'll always impute values that are plausible. So instead of instead of using like the linear regression model and then randomly adding a little bit of error to the estimate, randomly sampling from that distribution to add a little bit of error to that estimate, this is going to randomly sample individuals out of there and then impute based on what one of their values is. So it'll always be a plausible value in the model. I believe in there he even suggests, it's even good for categorical variables as well too. If you want to use predictive mean matching for categorical variables or dichotomous variables, you would need to change all the variable levels here for all of these variables to make them also scale in order to use predictive mean matching for that. And then I want to save out my imputations, and I'm just going to save it out to a data file that I'm calling imputed. You can name that whatever you want. I'm going to set a random number seed too, just to make sure if I want to run this again to get the same results, you can use that same number seed to get the same results I got. I'm going to run this, and then we'll be right back once it runs. It'll take it a minute to run. All right, so here's our imputation output. And so requested 20 imputations, same missing data patterns, and same information that we had before. We can go and open up the imputed data set. You can see it adds a variable called imputation underscore to the data set. And you can see it here. So imputation underscore 0 is the original data set you see with missing data. The imputation 1 is in the first imputed data set, and you'll see that this goes all the way down to 20 since we requested 20. So this is the 5th imputed data set. We could, in our syntax, open the data set. It's already open, so we might get a little error message. We could create, again, our dummy variables. So we got a little error because it was already open, but we can ignore it. And then to run the multiple imputation, you want to make sure that your cases are sorted by imputation. I always just go ahead and sort them just to be on the safe side. But by default, the file should already be sorted. So, but if you're doing any type of other data manipulation or analysis, data cleaning to that imputed data set, might be a good idea just to sort the cases just to make sure it is. And then for SPSS to recognize that it's an imputed data set, you have to use this split file command. And I like to use split file, and I want it the output to be layered by each imputation. So basically what this tells SPSS to do is to run this regression analysis for each one of these imputations. and then to pull results across each one of those imputations. So it's going to run a regression analysis on the original data set, on imputation data set 1, 2, 3, 4, all the way to 20. And then it's going to give us some pooled results as well. So it gives you a warning here. It says, the data set cannot be analyzed as multiple imputation unless the variable imputation underscore is defined in a split Filecoin. That was the first thing we did. That was the same thing I was talking about that we. So let's just scroll on up. So you can see here we get descriptive. So it does basically everything you request from your analysis. It then, gives you it for each imputed data set. There's the original. Here's where there was 130. Now we have complete K. Here's our complete K set. So we can look at how maybe the means for each one of the variables changes over each imputed data set. And then it'll give you pooled estimates. So where it's pulling the mean estimate across the 20 data sets. It'll do the same thing with the correlations there. This table is worthless. Here's our model summary. So we can see, what the R squared would be for the original data set, and here are the R squared values for each one of the imputed data sets. SPSS does not pull the R squared or adjusted R squared values for you. I'm not exactly sure why. Maybe because there aren't set pooling rules. If you're reading the literature about these, I think they call them Rubin's rules. He was the one who developed a lot of this multiple imputation procedures and developed rules for how you combine estimates across multiple imputations. What I typically do in cases like this is I'll report the average R squared and then give the range, then give the minimum and maximum across the imputed data sets. And then I would do the same thing for like the F statistics. I might just report the minimum and maximum F tests. Here you see they're all statistically significant, which isn't a surprise. So it's not as big of a deal, but you might just report maybe the min and max there in that case. So here we have our coefficient estimates for each one of the imputations, and then the pooled estimates here. You notice it doesn't pull standardized regression coefficients. You could calculate them by hand afterwards. A standardized regression coefficient is the unstandardized regression coefficient times the standard deviation of the explanatory variable divided by the standard deviation of the outcome. But then you got to figure, well, what's the standard deviation across the pooled estimate? So the other way you could do it is standardize, create z-scores for all of the variables, and then rerun the regression analysis with those standardized variables. So standardized reading, standardized writing, female, math, general, academic. Rerun the regression analysis, and then the unstandardized coefficients would be standardized coefficients. So if you really want those, that's one way of doing it. Here it gives you, SPS gives you some diagnostic statistics on the imputation. Scroll up to the top. So the first one's the fraction missing info, the relative increase in variance, and the relative efficiency. So we can go down here. So these kind of give us an indication of how well our imputation model is doing. So the fraction of missing information here is then the proportion of total sampling variance that's due to missing data. So if we look for, here we go, writing, we get 0.133. So that's saying that 13.3% of the total sampling variance is due to missing data. 13% of the sampling variance in writing scores is due to missing data. A really high fraction of information can indicate a problem with it, that's a problematic variable. A general rule of thumb that you might see out there is you typically want the percent, the fraction of missing information, the percent of that to at least equal the number of imputations. So if we find the highest fraction of missing information, that would be here with the general track. So we'd want this 20% to be at least equal to the number of imputations, which is 20. So the kind of the rule of thumb is you would take the fraction of missing information, divide it by the total number of imputations, and you want that to be equal to around 0.01. So that's why I say as long as they're roughly equal, then that's a generally decent rule of thumb. So like if you look here at this is the relative variance increase. So this is the estimated sampling variance. So for writing, it's 0.152. So that means that the estimated sampling variance for writing is 15% larger than its sampling variance would have been if the data were complete. So if we look at, for general here, the higher these values are, then that means the worse we're doing predicting that variable. So variables with large amounts of missing data, or variables that are weakly correlated with other variables, will tend to have larger relative increases in variance. So if we look at academic program for general, it's around 25% of the sampling variance is larger, so hold on, let me say that again. So the general academic program is its sampling variance is 25% larger than its sampling variance would have been if the data were complete. Generally what this would mean is that we're not doing a good job of predicting whether people are in the general academic program. The larger the fraction of missing information and the larger the relative variance increase is, the worse job we're doing predicting those variables. If we wanted these to come down a little bit more, this one isn't too bad. This one probably isn't too bad. I think that you'd want to see these less than maybe 20%. One thing we could do is we could try to find other auxiliary variables that maybe predict academic program. Remember, if we look back at our missing values analysis, we didn't do a good job of predicting missingness on the academic program. The other option we could do is just to increase the number of imputations. So instead of 20, increase it to 25, and we should see a decrease in the relative increase in variance. Here's our relative efficiency statistics. The closer these are to 1, the better the quality of the estimates are. So this is talking about the quality of the coefficient estimates. The closer they are to 1, the better the quality. Notice here, general still has the lowest value, so we're not doing as good of a job predicting it. Usually you get pretty good relative efficiency values with even just a few just a few imputations, 5 to 10. It usually takes a lot more imputations to for the variance estimates to become more stable. So that is then our quick introduction and kind of how you interpret some of the results for a multiple imputation analysis. Also in the syntax file, I give you some syntax how you could do a full information like maximum likelihood estimation on the same regression model we've been using. You would need a structural equation modeling package to do this. And here, I'm using the structural equation modeling package. It's the Laven package in R. I'm running R. There's a way you can run R through SPSS. The program is called Begin Program R. You give it the name of the library. We want to then open up the SEM program. I'm reading in my data set. I'm using a comma separated value because they're just easier to work with in R than an SPSS file. Here's my regression model. I want to regress reading on an intercept, writing, gender, math scores, general and academic. And here then I am fitting then a structural equation model using my regression model here, my data set, and I want to basically treat missing data using a maximum likelihood estimation. And then I'm going to print information about it and compute the R squared. So I'm not going to go into detail of how you actually do that. Let's see. Yep. Here you go. And so then it prints then, so you see in your output, in your SPSS output, it runs R in the background for you and then prints out the output in your SPSS output window. So we had 200 observations, 12 missing data patterns, and now here we get our estimate for reading. There's this, the coefficient, the standard error, the z-score, and the p-value. Same thing with, so you could then compare these maximum likelihood estimates with the complete case analysis and with the multiple imputation. Notice here, we didn't have to, here's the R squared for the model. Here, in this model, we didn't include any auxiliary variable, so we're only then imputing based on, we're not really imputing any missing values here. We're estimating the parameters of this regression model that are most likely to generate this observed data set. Also down here show you how, if you're really interested, here is a full information maximum likelihood estimation using the auxiliary variables too. I'm not going to go into information on it. If you want to talk more about that, we can. But you really need to know a little bit about structural equation modeling to kind of talk about some of that. But, as always, if you have questions, let me know. Post them on the message board. Email me. I'm always here to help. Thanks.